Welcome to this problem walkthrough. Today, we'll explore an interesting problem titled Time Needed to Inform All Employees. In this problem, we'll dive into a management hierarchy and figure out how long it takes to notify all employees. Let's begin our journey into solving this challenge. In this problem, we are tasked with determining how long it will take to inform all employees in a company about important news. The company is structured hierarchically, where every employee has exactly one direct manager, except for the head of the company, who has no manager. The hierarchy can be represented as a tree, with each employee being a node connected to their manager. The head of the company is identified by having a manager value of -1. To solve this problem, we are provided with two arrays: the manager array, which specifies the direct manager for each employee, and the inform time array, which indicates how long it takes for each employee to inform all their direct subordinates. Starting from the head of the company, our goal is to calculate the total time needed to ensure that every employee receives the news. The input to the problem includes the number of employees, n, which can be as large as 100,000. The manager array has a size equal to n and specifies the direct manager for each employee. Specifically, manager I is the index of the direct manager of employee I, and if manager I equals -1, it means that employee I is the head of the company. The inform time array, also of size n, tells us how long it takes for each employee to inform their direct subordinates. The output is a single integer representing the total time required to inform all employees in the company. Let's explore a few examples to understand this problem better. In the first example, the company has 6 employees, with the hierarchy represented by the manager array. Here, employee 2 is the head of the company because manager 2 equals -1. Employee 2 directly manages the other employees 0, 1, 3, 4, 5. According to the inform time array, it takes 1 unit of time for employee 2 to inform all their direct subordinates. Since none of these subordinates have their own subordinates, the entire process concludes after 1 unit of time, which is the output. This example demonstrates a simple situation where the head directly informs all employees in a single step. Now, in the second example, the hierarchy is more complex. There are 7 employees, and the head of the company is employee 0. Employee 0 directly informs employees 1 and 2, which takes 4 units of time. Employee 1 informs employees 3 and 4, adding 2 more units of time, for a total of 6 units so far. Meanwhile, employee 2 informs employees 5 and 6, adding 1 unit of time, but since this path is shorter, it doesn't affect the overall total. The longest path is the one where employee 0 informs employee 1, who then informs employees 3 and 4. This process takes 7 units of time in total, which is the output. The key here is to calculate the maximum time required along any path in the hierarchy. In the third example, the company consists of 4 employees, and the head is employee 2. Employee 2 informs employees 0, 1, and 3, which takes 2 units of time. None of these subordinates have their own subordinates, so the process ends after 2 units of time. When solving this problem, we must also consider edge cases. For instance, if there is only 1 employee, the total time required is 0 because there are no subordinates. If all employees have an inform time of 0, the total time is also 0 regardless of the hierarchy. In the case of a deep hierarchy, where employees form a chain, the total time is the sum of inform time values along the chain. For a wide hierarchy, where one manager directly oversees all employees, the total time is simply the inform time of the manager. These constraints and edge cases guide us in designing an efficient solution that can handle up to 100,000 employees. To solve this problem, we first consider a brute force approach. The intuition here is to simulate the process of informing employees by repeatedly traversing the management hierarchy. For each employee, we calculate the total time it takes to inform them by recursively moving up the chain, starting from their direct manager, then their manager's manager, and so on, until we reach the head of the company. While this method is straightforward and ensures correctness, it becomes computationally expensive for large organizations. The time complexity is O(n) squared, because for each employee, we could traverse the hierarchy of managers up to O(n) times, especially in cases with deep hierarchies. Additionally, the space complexity is O(1), excluding the recursive call stack. However, this brute force method is highly inefficient and impractical for larger inputs. To address these limitations, we turn to an optimized approach. Here, we model the problem as a graph traversal, with employees as nodes and edges representing the reporting relationships. By using algorithms like DFS or BFS, we can calculate the time needed to inform all employees in a single traversal, significantly reducing computational overhead. Now, let's break down the optimized approach. The first step is pre-processing, where we construct an adjacency list. This list maps each manager to their direct reports, making the hierarchy easier to traverse. Once the adjacency list is built, we perform a tree traversal starting from the head of the company, who is identified by the condition manager, I equals -1. Using either DFS or BFS, we propagate the informed time from the head down to each employee. In DFS, for example, the informed time of the current manager is added to the total time for each of their direct reports. This way, we efficiently account for the cascading nature of the informed times. The time complexity of this approach is O(n), as we process each node and edge exactly once. Similarly, the space complexity is O(n), accounting for the adjacency list and the stack or queue used during traversal. An alternative method to consider is using dynamic programming with memoization. Here, we store the informed time for each employee to avoid redundant calculations. While this avoids recalculations, it is functionally similar to DFS with added bookkeeping, so it doesn't offer a significant advantage. Both the DFS/BFS and DP approaches share the same O(n) time and space complexities. The strategy we choose to implement is the optimized approach using DFS or BFS. This method is efficient, straightforward, and aligns well with the problem structure as a tree traversal. Representing the hierarchy as an adjacency list simplifies the process of propagating informed times. Between the two traversal methods, BFS is slightly easier to implement iteratively, while DFS offers a clean and intuitive recursive solution. Both, however, are equally efficient in terms of time and space. There were a few key observations that guided this strategy. First, recognizing the problem as a tree traversal with the company head as the root was a pivotal insight. Second, understanding how informed times propagate in a cascading manner made DFS and BFS the natural choices for this problem. Finally, building the adjacency list upfront allowed us to avoid redundant calculations during traversal. When weighing trade-offs, the brute force approach was ruled out due to its prohibitive O(n)² complexity, making it impractical for large inputs. While dynamic programming is a valid alternative, it introduces unnecessary complexity compared to the direct DFS or BFS solutions. In conclusion, the DFS/BFS approach strikes the optimal balance between clarity and performance, making it the most effective solution for this problem. In this problem, we are tasked with determining the total time required to inform all employees in a company about a piece of news. The company is structured hierarchically, where each employee has exactly one manager, except for the head of the company, who has no manager. The news spreads from the head to their direct reports, and each report takes a fixed amount of time to be informed. To solve this, the first step is to represent the company's hierarchy as a tree. We can achieve this by parsing the input data to create an adjacency list. In this list, each manager points to a list of employees they manage. Additionally, we need to identify the head of the company, which is the root of the tree. This is typically the employee with no manager, indicated by a value of -1 in the input. Once the hierarchy is represented as a tree, the next step is to calculate the time required to propagate the news using a depth-first search, or DFS, approach. Starting from the root node, which represents the head of the company, we recursively calculate the time needed to inform all direct reports of each manager. For each direct report, we add the time it takes to inform them to the total propagation time for that manager and keep track of the maximum propagation time among all direct reports. This ensures that we capture the delay caused by the longest path in the hierarchy. Finally, the result of this DFS traversal from the root is the maximum time needed to inform all employees. It's also important to handle edge cases, such as when there are no employees, where the output should be 0, or when there's only one employee, where no time is needed. Additionally, leaf nodes, which are employees without subordinates, require no further propagation time. There are several key insights that make this approach both logical and efficient. First, Using an adjacency list to represent the hierarchy is beneficial because it allows constant time access to an employee's direct reports, making traversal much faster. Second, the recursive DFS method ensures that we systematically propagate the news through the hierarchy, focusing on one subtree at a time. By calculating the maximum propagation time for each subtree, we ensure that the slowest path is accounted for. This avoids redundant calculations and ensures an efficient solution. For data structures, the adjacency list is the core representation of the hierarchy. If we implement DFS iteratively, we use an explicit stack to keep track of nodes to visit. In the case of recursive DFS, the call stack handles this for us, making the traversal straightforward. Analyzing the complexity of this approach, the time complexity is O(n), where n is the number of employees, because we visit each employee exactly once during the DFS traversal. The space complexity is O(n) as well, due to the adjacency list representation of the hierarchy, and O(h) for the recursion stack, where h is the height of the tree. Let's walk through an example. Suppose the input specifies manager equals -1 0 0 1 1 2 2 and inform time equals 1 2 2 0 0 0 0. Here, employee 0 is the head, managing employees 1 and 2. Employee 1 manages 3 and 4, while employee 2 manages 5 and 6. Starting the DFS from the head, we calculate the propagation time for each branch. Informing employees 1 and 2 takes 2 units each. Employees 3, 4, 5, and 6 require no additional time as they are leaf nodes. The total time to inform everyone is 1 unit for the head plus the maximum of the propagation times, which is 1 plus max, 2 plus 0, 2 plus 0, equals 3 units. The output for this example is a total time of 3 units. This represents the time it takes for the news to propagate from the head of the company to the farthest subordinate. By focusing on the maximum propagation time at each level of the hierarchy, we ensure that the result accounts for the slowest path, which is the key to solving the problem accurately and efficiently. This Python implementation solves LeetCode problem number 1376, time needed to inform all employees, using a breadth-first search (BFS) approach. First, the number of minutes function takes 4 inputs: n, number of employees, head ID, the ID of the company head, manager, a list specifying each employee's manager, and inform time, the time each manager takes to inform their subordinates. The algorithm starts by constructing a tree-like structure using an adjacency list. The tree dictionary maps each manager to a list of their direct subordinates. This is achieved by iterating through the manager array. If an employee has a manager, not -1, they are added to that manager's list of subordinates in the tree. Once the tree is built, a BFS approach is used. A queue is initialized with the head of the company, ID head ID, and a starting elapsed time of 0. The BFS traverses the hierarchy level by level. For each employee dequeued, their elapsed time is compared to the current maximum time, max_time, to ensure that the longest propagation time is recorded. For each subordinate of the current employee, their elapsed time is calculated by adding the manager's inform time to the current time. This updated time is then appended to the queue for further processing. When the queue is empty, all employees have been processed, and max_time contains the total time required to inform all employees. This is returned as the result. The algorithm efficiently processes the hierarchy in O(n) time, as each employee is visited once. This approach ensures clarity and correctness, even for edge cases like an employee with no subordinates, leaf nodes, or a manager with 0 inform time. Here, we start by importing the necessary Java utilities and defining our solution class and method. The method, number of minutes, takes 4 parameters: the number of employees n, the ID of the head employee head ID, an array manager that maps each employee to their direct manager, and an array inform time that specifies the time each manager needs to inform their subordinates. The first step in our implementation is to build an adjacency list, which will represent the organizational hierarchy as a tree structure. This is achieved using a hash map, where each manager points to a list of their direct subordinates. We iterate through all employees, adding each one to the list of their respective manager. Next, we prepare for a breadth-first search, or BFS, by initializing a queue. Each element in the queue is an array containing 2 pieces of information: the current employee's ID and the elapsed time required to reach them. We start the BFS by adding the head of the organization to the queue with an initial elapsed time of 0. We also initialize a variable max time to track the maximum time required to inform all employees. Within the BFS loop, we process each employee by retrieving and removing the front of the queue. For the current employee, we update max time to ensure it always holds the largest elapsed time encountered so far. Then, we check if the current employee has any subordinates in the hierarchy. If they do, we iterate over their list of subordinates, adding each subordinate to the queue. For each subordinate, we calculate their elapsed time by adding the current employee's informed time to the elapsed time of their manager. Once all employees have been processed and the queue is empty, the maximum time required to inform all employees will be stored in max time. This value is then returned as the result of the method. This approach ensures that we efficiently calculate the time needed to inform all employees in the organization. In this example, we have a small company with 6 employees, where employee 2 is the head of the organization. The input provides the hierarchy through the manager array, where each element indicates the immediate manager of the employee at that index. For instance, employees 0, 1, 3, 4, and 5 all report to employee 2. To represent this hierarchy, we construct a tree structure using an adjacency list. Starting with an empty dictionary, we iterate through the manager array and add each employee to the list of their respective manager. Employee 2, being the head with no manager, is skipped. By the end of this process, we have a tree where node 2 has all other employees as its direct subordinates. This adjacency list will serve as the foundation for our BFS traversal to calculate the time needed to inform all employees. To begin the BFS traversal, we initialize a queue with the head of the company, employee 2, starting at time 0. We also initialize a variable max_time to track the maximum time required to inform all employees. Next, we process the employees level by level. First, we dequeue employee 2, who is at time 0. Since employee 2 has subordinates, we calculate the time to inform each of them by adding the informed time of employee 2, which is 1, to the current elapsed time. These subordinates employees 0, 1, 3, 4, and 5 are then added to the queue with their respective times. As we continue dequeuing employees from the queue, we find that none of the subordinates have further subordinates, so we simply update max_time as needed. By the end of the traversal, the maximum time recorded is 1, which means it takes 1 unit of time to inform all employees in this organization. In this larger example, we have 7 employees with a more complex hierarchy. Employee 6 is the head, while each other employee reports to the one immediately above them in the hierarchy. To represent this structure, we again use an adjacency list. Iterating through the manager array, we add each employee to the list of their manager. For instance, employee 0 reports to employee 1, so we add 0 to the list for key 1. Similarly, employee 1 reports to 2, so we add 1 to the list for key 2, and so on. The final tree reflects this chain-like structure, where every manager has exactly 1 subordinate except for the head. With the tree constructed, we initialize the BFS process with employee 6 at time 0, and max_time set to 0. Starting the BFS traversal, we first dequeue employee 6 at time 0. Since employee 6 has 1 subordinate, employee 5, we calculate the time to inform them as 0 plus the informed time of employee 6, which is 1. Employee 5 is then added to the queue with time 1. Next, we dequeue employee 5 at time 1, update max_time to 1, and add their subordinate, employee 4, to the queue with time 1 plus the informed time of employee 5, which is 2. This process continues as we traverse down the hierarchy. For each employee, we calculate the time to inform their subordinate by adding their informed time to the current elapsed time, and we update max_time accordingly. The traversal proceeds until we reach employee 2, who informs employee 1 at time 10. From employee 2, we calculate the time to inform their subordinate, employee 1, as 10 plus the informed time of employee 2, which is 5. Employee 1 is then added to the queue with time 15. Next, employee 1 informs their subordinate, employee 0, at time 15 plus their informed time of 6, resulting in time 21. Employee 0 is the last employee in the hierarchy, and since they have no subordinates, the traversal ends here. Throughout this process, max_time is updated whenever a greater elapsed time is encountered. The final value of max_time is 21, which is the total time required to inform all employees in this organization. In this trivial example, we have only one employee, who is also the head of the organization. Since there are no subordinates, there is no tree to build. The BFS process starts with the single employee at time 0 and max_time initialized to 0. During the traversal, we dequeue the head employee, but since they have no subordinates, no further processing is required. The traversal concludes immediately, and max_time remains 0. This means no time is needed to inform anyone, as there are no other employees in the organization. To summarize, the BFS approach allows us to efficiently calculate the time needed to inform all employees by traversing the hierarchy level by level. Using an adjacency list to represent the tree structure ensures that we can easily access the subordinates of each employee. The queue facilitates the level order traversal, while max_time keeps track of the maximum time encountered. This method processes each employee exactly once, resulting in a time complexity of O(n). Overall, this algorithm is well suited for solving the problem of determining the time needed to inform all employees in an organization. Here, we analyze the time complexity of our algorithm, which is O(n), where n represents the total number of employees. First, we consider the step where we build the hierarchy tree. This involves iterating through the list of employees from 0 to n1 and appending each employee to their manager's list in the adjacency list. Since this operation is O(1) for each employee, and there are n employees, constructing the tree takes O(n) time overall. Next, we perform a breadth-first search, or BFS, to traverse the hierarchy. During BFS, every employee is processed exactly once. Each employee is added to the queue once and removed from it once. Additionally, the BFS loop iterates through the subordinates of the current employee. In total, this amounts to processing all n employees, so BFS also runs in O(n) time. Lastly, we calculate the maximum time required to inform all employees. During BFS, updating the max_time variable is a constant time operation, O(1), and since this happens during each of the n iterations, it still contributes O(n) to the overall complexity. Together, these steps result in a time complexity of O(n). Combining the steps we just discussed, we see that the overall time complexity is O(n) for constructing the hierarchy, O(n) for BFS traversal, and O(n) for calculating the maximum time, which simplifies to O(n). Now, let's examine the space complexity, which is also O(n). The primary contributor to space usage is the adjacency list, which we use to represent the hierarchy of employees. In the worst case, the tree contains n1 edges, meaning the adjacency list stores O(n) relationships. This requires O(n) space. Additionally, the BFS queue can hold employees at the same level of the hierarchy. For example, in the worst-case scenario of a flat structure, where one manager oversees all employees directly, the queue could hold all n employees, adding another O(n) to space usage. Finally, variables like max_time and others used in the algorithm require constant space, O(1). When we combine these, the total space complexity becomes O(n) for the adjacency list, O(n) for the BFS queue, and O(1) for auxiliary variables, resulting in a total of O(n). Adding everything together, the total space complexity is O(n) from the adjacency list, O(n) from the BFS queue, and O(1) for the remaining variables, which simplifies to O(n). To better understand the efficiency of our algorithm, let's analyze different scenarios. In the best-case scenario, the hierarchy is shallow, such as a simple chain where each employee has only one subordinate. Here, BFS processes each employee once, so the time complexity remains O(n). In an average-case scenario, employees are evenly distributed across multiple levels of the hierarchy. Even in this case, BFS still processes each employee exactly once, so the time complexity doesn't change, it's still O(n). The worst-case scenario occurs with a flat hierarchy, where the head manager directly oversees all other employees. In this case, both the adjacency list and BFS require O(n) time and space, but the time complexity remains O(n). Regardless of the structure, the algorithm consistently achieves linear time complexity. To highlight why this solution is optimal, let's compare it to a brute force or naive approach. In a naive solution, we might recursively calculate the time needed for each employee to be informed by traversing the hierarchy upwards to the head for every employee. This would result in a time complexity of O(n) squared, in the worst case, as each of the n employees could require a traversal of O(n). For example, in a flat hierarchy, we would effectively repeat the same O(n) traversal for each employee. By contrast, the optimized solution avoids this inefficiency. It builds the hierarchy once using an adjacency list and processes employees with BFS, ensuring that each employee is handled exactly once. This reduces the time complexity to O(n). Space usage is also more efficient, as the adjacency list and queue require O(n) space compared to the potentially large stack space needed for recursion in a naive approach. Finally, we can prove the algorithm's linear complexity mathematically. Constructing the adjacency list is O(n), BFS traversal is O(n), and the space usage is proportional to the number of employees and relationships, O(n). Therefore, both time and space complexity are O(n), making this solution highly efficient. When solving this problem, there are several common mistakes to watch out for. First, not handling edge cases properly can lead to runtime errors. For instance, scenarios like an empty input, a single employee with no manager, or even a disconnected graph structure need to be carefully considered. Always validate your input constraints before diving into the implementation. Another frequent mistake is using inefficient recursive traversals. Overusing recursion without memoization can result in redundant calculations, which can significantly increase the time complexity, potentially to exponential levels. For tree-related problems, caching intermediate results using techniques like dynamic programming can be a game-changer. Similarly, forgetting to define or properly implement the base case in recursive solutions can lead to infinite recursion or incorrect outputs. Always ensure your base case is aligned with the problem's constraints. Finally, a common source of errors is confusion between parent and child relationships within the structure. Misinterpreting these relationships can lead to incorrect tree traversal or computations, so make sure to carefully map out the hierarchy before you start coding. Now, another critical mistake is ignoring the constraints on time limits. It's essential to test your solution not just on small, simple inputs but also on large datasets that simulate worst-case scenarios. Neglecting this can result in time limit exceeded errors during submission. To avoid this, always analyze the time complexity of your solution and ensure it scales efficiently. On the interview front, understanding the core structure of the problem is vital. Many hierarchical problems can be modeled as trees or graphs, and recognizing this early on helps you select the right traversal technique, whether it's breadth-first search, depth-first search, or even topological sorting. Additionally, optimizing for scalability is a key consideration. Interviewers often evaluate how well your solution handles larger inputs, so incorporating dynamic programming, memoization, or iterative approaches can help eliminate redundant calculations. It's equally important to communicate your approach clearly. As you code, explain the trade-offs between different methods, such as brute force versus optimized solutions, and demonstrate your awareness of edge cases and constraints. Using the right data structures can simplify the implementation of problems involving hierarchical relationships. For example, adjacency lists or hash maps are excellent for representing parent-child relationships, and pre-computing additional arrays, such as those for cumulative costs, can minimize computation time during traversal. To build a deeper understanding of this problem type, you might want to explore related problems. For instance, LeetCode 1376, which focuses on informed times in a management tree, is a direct application of hierarchical traversal. LeetCode 310, which deals with finding minimum height trees, is another tree or graph-based problem that requires optimization for efficiency. LeetCode 841, focusing on reachability in a graph, and LeetCode 207, a topological sorting problem involving course prerequisites, are also highly relevant. These related problems can help you strengthen your ability to handle various traversal scenarios and deepen your understanding of graph and tree structures. When it comes to alternative approaches, each has its own pros and cons depending on the problem structure. Depth-first search with memoization is a powerful technique for hierarchical problems, as it avoids redundant calculations and ensures efficiency. However, it does come with increased memory usage due to the recursive stack and the memoization table. Breadth-first search, implemented iteratively, is another strong option. It eliminates the risk of a stack overflow associated with recursion and is particularly effective for iterative processing. That said, it may require additional data structures, such as queues, which can make the implementation slightly more complex. Finally, if the problem can be modeled as a directed acyclic graph, topological sorting is an excellent choice. It ensures that dependencies are processed in the correct order. However, this approach is limited to problems that fit the DAG structure, so it's not universally applicable. Understanding these trade-offs will help you choose the best approach for the specific constraints and requirements of the problem at hand. Great job making it to the end. In this session, we tackled the problem of informing all employees, starting with a brute force approach. Remember the importance of analyzing input structures and considering optimized traversal techniques like DFS or BFS. Thanks for watching, and see you in the next walkthrough. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!